Thank you guys for stopping by. So like Franklin mentioned, today we're gonna talk about a case study on how we built and evaluate our prompts on production grade dataset. The talk specifically is gonna be focusing on entity extraction and reprompting. But we're hoping that the framework and the thinking is gonna be able to inspire you to do kind of similar work in other use cases as well. Okay, so before we start, both Bhuvana and I work for a company called Voiceflow. The reason I'm saying this is because I want to give you some context as to, so that the examples we're going to use are going to make sense to you. It is a platform for teams to build and launch their AI chatbots. So the company falls into industry called conversational AI, or CAI for short. And what we're going to cover today is we're going to start by framing the problem statement, like what was the problem we're trying to solve, and then lead to a brief history of entity extraction before, all the way leading up to LM. And our first attempt at solving it by hand and how that went. And the second attempt to try to solve it like an engineer, and then walking you through the exact metrics and pipeline we used in the technical implementation. And the end is going to show you some benchmark results from all the attempts that we tried throughout this process. Okay, starting with the problem statement. So in conversational AI industry, we deal with two main tasks for machine learning. The first one is intent classification. So that's your typical multi-class classification problem. So say, for example, if a user asks a question in a chatbot online, I want to book a flight ticket to Vancouver next month. Do you still have any ticket available? We want to be able to match that to a particular intent. In this case, it would be like the book flight intent, for example. So then the bot can take you to the relevant dialog flow that's related to that particular intent. Now, the other side of the issue is anti-extraction, which is what we're going to talk about today. And then in the machine learning words, it will be name entity recognition. So in that exact same phrase, what we potentially want to extract from here, which is the Vancouver as a city, and then next month at the date for entities. Now, a little bit different from traditional NER, there's a unique challenge in conversational AI, which is the reprompting problem, right? Because like I'm not feeding it a paragraph or a article, right? Like it's already pre-written, and then you can just extract the entities as you go through the article. It's a conversation, right? And sometimes users don't always give you the answers that you're asking for. Say, for example, in the previous statement, let's say somehow they forgot to say the city name, right? Vancouver is not there. Then there are multiple ways we can handle this problem. Traditionally, what we do is the conversational designer is going to put in some kind of a manual or a static response. So sorry, I didn't catch it. Which city did you want to go to? And if you keep refusing to answer the question for some reason, then you would basically see the same thing getting repeated over and over again, right? That's not a great user response. You can clearly tell it's a bot. Now, the second one is slightly smarter so that we can sort of have some kind of if-else there. We can use guided plus rules. Like, for example, we can give some variance to what you would say. What city do you want to visit? Or I forgot to grab the location or something like that. But it's still kind of, like manual input there, right? Until recently, we can use the LM-driven approach, which is you basically give it a prompt, and then you tell the LM what you want it to capture or you want kind of the scenario to be, and then you can prompt the user for a city they may want to visit, right? And then you get a response that's a lot more natural sounding. So the goal for us to explore here is to how can we improve the performance of anti-extraction and reprompting using LLMs, and then using a way that is measurable before we kind of launch this feature into production. An example task here would be, say, for example, you want to conversationally ask a user for their information, right? Their email and their phone number. There's some additional complexity to it other than what we already talked about. The baseline is we want the response to sound natural and with enough variance. The first one is that users don't always give you a straight answer, right? It's difficult to kind of preemptively think what are the paths they are going to potentially take, right? And plan for all of them. Then the second complexity is some additional rules that you may have. Let's say, for example, it's a chatbot for booking business demos for like your potential customers. Then you may only want to look for business emails instead of like regular personal emails, right? And that's like additional rule that may make the extraction a little bit more difficult because some emails automatically is not going to be invalid, right? The third one is some kind of like overuse or a security prevention. Let's say I'm trolling somebody's bot and I'm never going to give the answer. I'll just keep doing, asking the question and kind of load your server over and over again. You want to have some prevention there to, let's say, I want to end the conversation if it's not going anywhere after a certain number of turns, right? So that's like additional measure you potentially want to put in. Okay, now with the kind of problem statement in mind, now let's kind of take another turn looking at the history of entity extraction. What are the things we've done before? Starting from the early 2000s, so that's when we started having kind of these rule-based parsing. So what they do is like you kind of tag the entities with some tool, and then you look at the software itself is going to be looking at kind of the sentence structure, and therefore parsing the particular entities you have enough examples of. And by that time, we already achieved like pretty decent precision and recall and F1 score, but is entity recognition resolved at that time? I wish, but it's not. And also this is like 20-something years ago. It's really making me feel old. Then fast forward to about a couple years ago, right before LM became a thing. The dominant one at that time was mostly just encoder based, so some kind of like fine-tuned BERT model. It was doing pretty well. Like it was able to handle a lot more complex sentences with different varying like structures, and also a lot of model support multi-language as well. There were like some novel ideas of how you can essentially not only just treat the sentence as the entities, but then also add on to the label of the entities and kind of train them together by constructing the similar classes together and then dissimilar classes further. It was doing like decently well. But it also obviously had very serious cons there, right? Like as any BERT model, we have a limit context window, which is 512 tokens. It's not a lot of words you can put in. And a lot of out of the box model, like unless your industry is like so commonly like widely adopted, it's not very good performing. So you need some kind of fine tuning. So that will require you to gather your own data that's good, like well labeled, which we all know is a pain. And then you need GPUs to train the model, and then you are not still like not sure if it's going to be performing well in different use cases. Especially this just this pain, which is the alt domain, which is like if I'm training my data with all these classes, but then when I'm doing inference and I put in these unseen labels, it usually performs pretty terribly, right? So all of these are kind of unresolved issue back then. And then LM happened. Thank God, it just saved my life, because that NER has been the bane of my existence working as a machine learning engineer. So now we can easily just like tell LM a prompt like, okay, you are information capturing device. Now help me capture this information. And it's a lot better performing. I don't need to do all those training and spend lots of dollars on training my model. It's a lot easier now. Okay, so now that brings us to essentially our first attempt of trying to solve this problem using LM by hand, right? Because like we think we're good engineers, like we can definitely do this, right? So okay, what do we need LM to do, right? We need LM to be able to support cross-domain entity, right? Because like Voiceflow, we have like over 250,000 users. There's probably thousands of different use cases. We need it to be able to handle this feature, to be able to handle a lot of different use cases, right? It needs to have natural sounding response, also multi-domain use cases, even within the same bot. Let's say if it's covering a banking, there's a credit card side of business, and you also have the personal banking need to be covered multi-domain as well, performing equally well. And then especially the smart reprompting when users aren't being straightforward for whatever reason. And it also needs to easy to build, right? We don't need all the resources that I talked about, right? Like we can just pick it up and like start doing something about it. Okay, so then we gathered all the best engineers and we sat down, we kind of collectively reorganized all the prompt engineering best practices we can think of. And this is what we came up with, right? So like we know LM has kind of this tendency to taper off, prefer to take picture. wait until you see how the results went, right? We put the like crystal clear ask at the very beginning, right? And like specify the format and the access scenario, all of that stuff. We use a few shot examples to give it 2 clear examples with the very well defined rules and entities and transcript, not like what the expected output, right? And it's like, should be great, awesome. Okay, let's put it to test. Let's scale up to a test data set with enough data to see how well it does perform. Pretty not okay. I would say definitely not okay enough to push it to production. Awesome, okay. Let the bruised ego aside. What can we do better? Okay, so then we regrouped, and that's where we start thinking about, okay, we gotta think of a better way to like potentially hand test the thing, right? Like over and over again, and hoping it's gonna give us some better results. So our second attempt is we are trying to solve it programmatically, right? So we start to define schema because we need this to be reproducible. We need this to be scalable. What we started is 2 parts, right? We need the conversation or the transcript, like what we expect for the conversation to go. And the second part is the additional rules and the task itself, right? So for the transcript itself, now each block under the transcript stands for a particular turn of the user and the system's response. So say, for example, the first one is I want to get a driver's license, and the model response could be, yeah, definitely, but could you please tell me how old you are, right? And then we have this type here that says whether the action needed is a reprompt because you didn't give me the age, because that's what we needed to fulfill the entity, or is it fulfilled if you did indeed give me the age, right? And then the rationale just for some chain of thought reasoning that we can evaluate as well. The additional rules here, this is basically obviously particular to your task, but like what we had is, for example, the individual must be at least 16 years old in order to get a driver's license, right? And then you have all the exit scenarios of, let's say, if they are less than 16 years old, or entity is captured, or if they somehow refuse to provide their age for whatever reason, right? And the also entity examples of what it could look like, right? So when we tried that, by hand still at this stage, we do see some examples of failure and success. Like for example, if I just say 21 years old, so the example response we're expecting, which is kind of what we want the system to prompt, is like, you shouldn't say anything because you already, the entity is already there, just capture it. But what ended up happening is, which is a predicted response, is sometimes they just somehow think it's not there. So they'll still keep asking you to provide the information. And then as you can see, like the entity is already captured, but then like it gives you the wrong predicted type. But sometimes it just works seamlessly, right? And we just need to figure out a way, like for example, this is like getting the contact information, and then it didn't have the phone number, therefore, both were expecting it to reprompt. And you can already tell it's like evaluating this is gonna, like if you try to do this by hand or just eyeballing it, it's gonna be difficult, right? Because like we're trying to evaluate the differences between the example and the predicted, right? Like it's not just about either similarity or whatever. Like you need a way to semantically understand the meaning and to be able to compare the accuracy, right? So that brought us to this great framework. It's called DSPY. I believe it is a framework developed by Stanford, and I think it's out for, I want to say, a year and a half now. It is a great framework to evaluate the prompt and optimization. So like if you're familiar with PyTorch, which is basically optimizing the weights for training neural nets, this is like similar concept, but then like for training, for optimizing the weights for prompt. Okay, now I'm gonna pass it to my coworker Bhuvana, who's gonna talk you through the exact pipeline and metrics that we use for this framework.
Thanks, Yoyo. I hope you can hear me clearly. Okay, cool. Okay, so this is where the presentation is going to get more technical. Yeah, as Yoyo mentioned, DSPY is a great framework. It's based on written in Python, and it lets you program the language model. And instead of handcrafting the prompts, you can programmatically evaluate the prompts. And another advantage of DSPY is that it's based out of declarative programming, where the user or programmer need not actually worry about how to accomplish this at any task, rather what to do. Like what is that I need to do in order to derive at a prompt that works really well. Okay, so once we decided on using DSPY as our framework, we had to define what are all our inputs and outputs. So yeah, inputs. We'll go through each and every component of input in detail, but I'll just give an overview, like a high-level overview of what are all the inputs that we considered. One is signature and metrics. So think of signature as like in telling your LLM what is the intended behavior. Say you are a customer support agent. So what's the expected behavior from an LLM? So that constitutes the signature. And when it comes to metrics, is more or less like, how do you evaluate the prompts? Next is the data schema. So we already saw the schema that we defined for this exercise or experiment. And next comes the data. So we had to ensure the data conforms to the data schema that we already defined. The important piece here, I would say, is prompt improvement algorithm, which is commonly known as teleprompter or optimizer in DSPY. So this is the one which is going to evaluate the prompts based on the metric results. And the outputs are pretty straightforward. You get a score and a prompt, and then you choose the best prompt based on the highest score. So yeah, overall, this is how the pipeline looked. So the trained data would comply with the data schema that we already defined, and the signature kinds of reads this trained data, because the signature need to know what are all the inputs and the expected output from an LLM. Both are then fed into the compiler. So the compiler is gonna optimize the prompts so that you achieve the best evaluation metric. Once we have an optimized prompt, the data is now tested against the evaluation data set, and then we pick the highest score and the prompt associated with the score. Yeah, let's go through signature in detail. As mentioned earlier, so signature is the one kind of it tells the LLM the expected behavior. The input and output are part of the signature. So DSPY does provide basic signature formats, but in our case, we had to define our own custom signature. So here is an example of the signature that we define. One is the user statement or the user utterance. So that's the input from the user. Next are the rules. So using which you will evaluate the user response or the user utterance based on the defined rules. Example entities, that kind of tells LLM, so these are all the entities that I expect. For example, I'm 21 years old. The example entity would be age and then a random value. And captured entity state is the output, which would say what is this entity that is captured, whether it is age, and also like what is the state of the conversation. Is it fulfilled or a reprompt is required? That also constitutes the output. Here is the interesting part, which is the trained data. So in our case, Voiceflow, we support 14 or 15 entity types. But when we look at the production data set, like we couldn't find much data for data types like ordinal or percentage. So that's a challenge. One way to kind of overcome this is using synthesizers. So DSPY does provide some options to synthesize data, or other straightforward approach was just use an LLM like GPT-4. So these are all some of the examples I have. Why don't you generate more examples for, like, say, ordinal or percentage? Yeah, so next is the important piece, as I mentioned, the compiler part. So compiler is actually the teleprompter or optimizer that we saw earlier. So that's gonna take an input program, a training data, and then a metrics. And then it is going to optimize the program so that you achieve the maximum metric. So that's the compiler. So we used Bootstrap Few-Shot. So interesting thing about this Bootstrap Few-Shot is, let's say you don't have much training data. Let's say you just have 10 training data for this experiment. What does Bootstrap Few-Shot do is, it will make 10 LLM API inference calls and then use this data and then use your pipeline to generate demonstrations. And it will only use the demonstrations which pass a certain metric. So that's the advantage of using Bootstrap Few-Shot here. Okay, next is the metric. Metric is pretty straightforward. You have an expected value, and then you have the actual value. You compare both and then see how good is your actual value when compared to your expected value. In our case, like we kind of defined our own custom metrics. So we split them into 4 different metrics. One is the LLM response match. Like if you recollect the example from Yoyo, what is the expected response from LLM? What is the actual response? This is more like a similarity score. Next is the rationale match, which is what is the reasoning behind providing that response? More like, again, this is also a similarity score. The next is the entity state match, where we capture the entity keys and values. Let's say age, value is 21. So this is more like a JSON file, or a JSON format, where you compare all the expected entities are captured, and then you have the value associated with it. And finally, the response type, which is this a fulfilled one or a reprompt one? One quick advantage here, again, I would say, is we were able to add weights on different pieces of metrics. For example, in our case, the entity state and response type, we added more weights to that, so that, because that's what we were looking for to optimize. Yeah, next comes running benchmarks. So evaluation data, as a rule of thumb, like we used 80-20 split. So our training data set was like around 400, so validation set was 100 and evaluation 100. So the Bootstrap Few Shot, we can also provide validation set as an input, so that it performs well even during the optimizer phase on the unseen data. So once you have the optimized prompt, you would run it on this evaluation data set and then determine what works best. Yeah, the final piece is scoring. As such, like these were the results that we had as part of our scoring metrics. So the first one was handcrafted. The overall training score was just 58.7. The next one was using chain of thought with 0-shot examples, like where you don't provide any examples at all. It performed little better over the first one, which was handcrafted. And we were able to achieve much better performance with Bootstrap Few Shot. And the maximum performance we were able to attain was using hand few shot, because so there is a way you can override Bootstrap Few Shot with your own hand-picked example. So the way Bootstrap Few Shot optimizer works is it tries to pick the best few shot examples that will maximize the metric output for you. So using hand few shots, what you can do is you can override the list of few shot examples that Bootstrap Few Shot would use. And we kind of used some of the examples ourselves, like handcrafted examples for some of the built-in entity types. And that was able to provide us an overall score of 93.0 on our training data set. Yeah, so in summary, I think we covered framing the problem, and then what brought us to DSPY, and how did we kind of run this experiment using DSPY. And yeah, and that completes our talk. Thank you so much.
Any questions?
Hi, thank you for the very interesting talk. I see in your evaluation metrics you have used ChatGPT models. So the entity, or especially NARs, can be more specific when you are targeting a specific type of model for a specific type of problem, right? So for example, topic modeling, you use bird topic and things like that. So have you tested something specific like that as well for the problem that you are framing?
Yeah, so we're lucky enough that for conversations, it's a pretty generalized use case. So like GPT models were performing really well, but we did try some other, they all had similar performance. And then GPT is just widely available. And that's, it's the cheapest cost for us at the time. That's why we chose that.
Yeah, thank you for the great sharing. So NER is kind of a sensitive data. Do you have any practice to anonymize or just keep the data safe?
Yeah, so I think you're more talking about PII. So NER is not necessarily PII. But just for that particular PI piece, because we're a platform, so we don't really we don't see customer data, so it will be up to the customer. We can give them like support or like direction, but it will be up to them like how they treat the sensitive data. We don't have access to the customer's bot at all.
But you are exposing the identity data to the GPT, right?
Yeah, so that's actually a big concern because like if they, so this is opt-in feature. So first of all, this feature is not in production yet, but it is an opt-in feature. So we understand the kind of concern of companies, especially for like healthcare or banking for using LLM. So like we want to make it actually clear, like you need to specifically opt in to be able to use it. And then just to address that concern, like what we found is like some customer, for example, prefer to use, let's say, Azure's GPT API for like better data privacy practice. So like then we'll give them that option.
Thank you very much.
We still have, I mean, just to add to it, like we still have the option to choose plain NLU or hybrid model, like where you kind of pass it on to LLM as well.
Yeah, thank you for your presentation. So how do you evaluate the rational match score, given that the predicted rational will vary with each epoch of running the model due to behavior of LLM?
Sorry. So you're asking how did we derive at the rational metric score?
Yeah. Because, you know, do you set the temperature like to 0? Because each time that you run the model, you will get a different predicted rational from the model, right? So how do you evaluate and give the score to the predicted rational?
Yeah, so on the temperature setting, I think we did not change it for every iteration. And rational as such, like you're trying to understand what's the reasoning behind a response provided by an LLM.
Yeah.
So it's more like a similarity score. And as I mentioned, we kind of used weights to determine which is the important metric. So the response and rationale, we kind of understand it's more like similarity score, and then it might vary depending on, you know, the settings that we have. But we kind of focused more on the other two, which is the actual entity captured and then the state, like whether it's fulfilled or pre-prompt. So that was like, that's how we kind of weighted more on that particular metric piece.
Yeah. Because we can't rely on this metric, I think, because it will vary in different iterations. Yeah.
So semantic meaning usually don't vary that much. Like the way you say it could vary, but like your meaning shouldn't vary that much, right? So like even if you don't control, like obviously for reproducibility, you want to keep all the variables kind of consistent. But like say, for example, if I say, I didn't get your name, or say you forgot to say your name, even though like the literal like wording are very different, but like they actually mean the same thing.
Yeah, the semantically,
Yeah,
but
exactly.
it's really hard to get the semantic behind the iteration. Yeah.
So I think the similarity score is basically translate the sentence into some kind of like semantic vectoring space. So then you're actually like, it's not a word-to-word similarity, it's more like semantic similarity.
Yeah, thank you.
Yeah.
Just one more quick question. How do you convert it to semantic meaning, to its semantic?
It's built in with DSPI, PY.
Okay.
Like you can specify like what kind of metric you want to use in that framework.
Okay, thank you.
Awesome. No more questions.
Thank you.
Thank you.